Okay, so our first talk is from Warren Pickett. Warren has been, Warren has worked many years on superconductivity, theory of superconductivity, and materials in particular, band structure and predictions, and hydrides. So I look forward to your talk, so please go ahead. This is a pointer, and oh yeah, and the down arrow is the advance. Oh, you have your own. Okay, that's what. Yep. It works. Yeah, we checked. Oops.
All right. Welcome, everybody. Am I coming through loudly? So I was told that this winter school has, before this year, always been mostly on synthesis and characterization. This year it's on high pressure, but I said I could talk about synthesis and characterization of the theory of superconductivity. So that's the reason for this strange title. So I have given this talk, similar talk, several times, about 2 or 3 years into this era of near room temperature superconductivity and compressed hydrides. It became clear to me that there were a lot of groups doing calculations using these sophisticated codes to calculate TC in these hydrides that didn't have much knowledge of the history of the theory of superconductivity or just what was in the codes. So that's why I wrote this Reviews of Modern Physics article that came out finally this year. And I'm going to cover briefly sort of the first half of what's in that article and kind of a show and tell fashion here. There's going to be some equations here and there. For the most part, when you are studying physics and encounter equations, the equation should talk to you and tell you something. You should understand what the equation is saying. You don't need to worry about that here. The equations here are for just display purposes. Okay, so here is, let's get my, this is not,
May have to use
okay. This is the poster for a workshop in 2005 held at Notre Dame University called The Possibility of Room Temperature Superconductivity. And since then, I've seen probably 8 workshops with this sort of emphasis, and I've attended 4 of them, I think. Very interesting workshop, no outlandish ideas presented, and as far as I know, nothing big came out of it, but it's a nice big poster for the idea of room temperature superconductivity, which has been around since the time I was a graduate student, which is a long time ago. So I've given this talk at here. This was a previous talk was at the Pacific Rim Institute, which was hosted in South Korea. This was during COVID times. I gave the talk in South Korea, in Brazil, in Germany, and also at San Diego virtually, and a couple of times since then. So let's begin. You've all seen applications of superconductivity like this. So I'll have a few slides in here that go by quickly. This is a demonstration of superconductivity in a lab, actually a demonstration lab at UC Davis. And this is Valentin right here. Right here. And I'm really acknowledging my two postdocs, Yunde Kwan and Soham Ghosh, right here in this figure, and his undergraduate student who handled the liquid nitrogen. This is a magnetic track with a puck of YBCO on it, where you can start it and let it go round and round, and you can even let it go round and round below, because the flux is trapped in the superconductor. So let me just switch to something briefly. And this is really intended to be brief, not the full length.
It goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen.
Is real.
Systems for clean rooms.
So here it's just illustrating at the end of this that you could have a track like this, superconducting track, which will carry your liquid nitrogen model around from lab to lab outside the building like this. All right. So you can do lots of things with these demonstrations. All right, let's get on with the talk. In the beginning, superconductivity was discovered by Cameron and Otis in 1911, Fort Kelvin. I keep hitting the wrong button here, sorry. And this was the progression of the maximum TC up until 1970, when it stopped for a while. Niobium-310 and related A15 materials had the highest TCs here. And just to go through briefly what we're going to touch on as we go through the talk. In 1973, Bruce Friday presented a letter to Physics Today of 3 or 4 paragraphs maximum, because it had been so disappointing since 1957 up until 1973. There had been a lot of work around the world on materials, trying to find new superconductors, trying to perfect superconductors and get higher TC. And in 20 years, there had been an increase of 6 Kelvin in the maximum TC. And what Bruce Friday said was, if you plot these like this, you can see the straight line, and we're going to hit room temperature at the year 2840. So just eat right and exercise and hang around. So we'll get into the theory of superconductivity, Migdal-Eliashberg theory. Here, that was much earlier, that was 1960, but the computational theory really grew up in this time period around the turn of the century. Then in 2014, Chan Sui predicted computationally TC of 200 Kelvin in hydrogen-3 sulfide around 200K at 200 gigapascal. Sorry, the second one is 200 gigapascal, which is really a crazy prediction because this is electron-phonon superconductivity, and the maximum at this time was MGB2. Itself a surprise. In 2001, it was discovered. Then in 2015, shortly after the prediction, Hermitz's group announced the discovery, the real discovery of TC of 200 Kelvin at around 160 gigapascal. Quite reasonable agreement with this prediction. And then in 2019, Hemley's group and then Hermitz's group announced TC of 250 to 260 Kelvin in lanthanum hydrogen-10. So we're going to go through the history of the development of superconductivity and hit a little bit on the materials toward the end. So this is just, you've seen these plots. First of all, the maximum TC at a given time, which the previous plot showed this part, and these are just the big discoveries since then. finally up to the hydrides here. Okay, so let's start off with superconductivity. What is superconductivity? And it is mostly described, almost entirely described in the physics literature, as the breaking of U1 symmetry of the system. U1 is the unitary group of one in one dimension. Unitary means complex numbers. I'll say a little bit more about this in the next slide. And it's related to charge conservation. Just a little bit more background. Superconductivity in general deals with phase transitions, and a phase transition occurs when you go from a higher symmetry system to a lower symmetry system. You break some symmetry, and in superconductivity, it's always, what happens here? It's always U1 symmetry, but it could be the space group symmetry, called L here, spin rotation symmetry, time reversal symmetry, inversion symmetry, or some other symmetries that you have. There are other symmetries in a crystal which seem trivial. And for exotic superconductors, you break not only U1, but you break some of these others, one or more of these others. We're not talking about those. So what is gauge symmetry? It's a unitary group in one dimension. Unitary means complex numbers. And, well, it involves complex numbers. And dealing in terms of second quantized operators C and C dagger. C destroys an electron in a given state, given by subscripts. Subscripts aren't presented here. And this is the creation operator. And what U1 symmetry is that you map C onto C times a complex number, e to the I phi. And therefore C dagger, which is the Hermitian conjugate, goes to the complex conjugate of that number times itself again. And if you have, if you have a pair like C dagger C, like a number operator, for example, then it maps onto itself. And if you have an interaction which involves, my pointer seems to not be pointing, C dagger C, C dagger C, it maps, you can see the complex numbers. There's no worrying about commutation. And, okay, so we'll have to see if I can still change. Maps onto itself. It's trivial, okay? So a Hamiltonian involves which one of these?
Yeah, down arrow is advance.
The light, okay. So the Hamiltonian involves pairs of operators, C dagger C, and quadruples, which is interactions, C dagger C, and this is invariant under the U1 group. So broken symmetry involves this. In quantum mechanics, where you deal with n-particle states, we start with n equals 1 in quantum mechanics. Then if you destroy a particle in this, state of fixed number of particles, capital N, you get a state with one fewer particles, and then another factor of C, the expectation value is 0, because there's no matrix element of that operator between pairs of states of same particle number. But in the grand canonical ensemble that we deal with a lot in condensed matter physics, we have connections between n particle states and n minus 2 particle states, and there can be a non-zero expectation value here. And superconductivity involves supposing that there is a non-zero expectation value of this product of 2 annihilation operators or 2 creation operators, and that is the order parameter that exists below the critical temperature Tc. and it's equal to 0 in the normal state, and it's non-zero in the superconducting state. So this rather trivial transformation here is the way it shows up in canonical ensemble, grand canonical ensemble. Okay. So, okay. So this is, again, the group of operations, which is broken by superconductivity. And I probably don't need to go through all of this because I'm not going to talk about type 2 superconductors, in which there are vortices, and the critical temperature of those has usually been below 40 K for phonon-coupled superconductors until these hydrides were discovered. Okay, so the theory, starting from the beginning and coming up to the present. I've added 2 slides to my previous talks because they're part of the theory of superconductivity. They're not part of the current theory of what we call Migdal-Ili-Ashburg theory, but still, in 1935 and 36, the two brothers I'm going the wrong way. I'm always going forward here. Okay, the two brothers, London, Fritz, and Heinz, who were in Oxford at the time, heard about the Meissner effect, that Meissner and Oschenfeld had shown that a superconducting sample excludes the magnetic field. If the magnetic field, if it's become superconducting, or if it's superconducting and you bring a magnetic field, it excludes it. That's the Meissner effect. And they use this together with the fact that, as already known, the superconductor has 0 resistivity to posit a superfluid density in sub S and how it reacts to electric and magnetic fields and gives rise to a supercurrent J sub S here. So that is still the case in peculiar superconductors that experimentalists try to identify this superfluid density. There's, in good band materials, there's a more modern definition of what that is. In 1950, Ginsburg and Landau put together this phenomenological theory of the superconducting state, in which psi here is a complex valued superconducting order parameter, whatever that means. It's whatever describes what's happening in the superconductor. And it becomes non-zero below the critical temperature. So you have a free energy expansion like this, which is the free energy in the normal state, which is going to be continuous across the phase transition and not of interest. And then you have an expansion in this small parameter, order parameter, below but near TC. And this is just a power series expansion right here. And then there's a kinetic energy term, which comes from quantum mechanics, but it also comes from classical mechanics, where you put the vector potential in here for the external field, and B is del cross A. And this is the free energy functional, one of the free energy functionals, but it's the one for a bulk superconductor in a magnetic field B. And then you minimize that with respect to the order parameter and with respect to what other variables are in the problem, and you get a series of equations which you solve and analyze, and they describe many things correctly. 2 length parameters in the theory are the coherence length and the penetration depth. And this sort of theory is still used a lot for types of superconductivity that we don't really understand. Here is Abrikosov in 1958, used these equations and determined that in a type 2 superconductor, where you have vortices in the superconductor, you have what is now called the Abrikosov vortex lattice, and this is a simulation. This is a simulation of one, not an actual picture, but you can get real actual pictures with iron filings and with superconductors in the magnetic field. This is BCS theory, 1957. Bardeen, Cooper, and Schrieffer. It's a really impressive paper, 29 pages, 275 numbered equations. And it gave a completely new picture of superconductivity. Not there was a really great picture before. Not only that, it used a correlated wave function approach, which was extremely new to theory at that time, to do this. And assuming you just have a usual metal, takes me time to get used to, and making a model Hamiltonian, which assumes that there's pairing right here, attractive interaction due to, they knew it was phonons at that time, they knew it was related to phonons because an isotope effect has been measured. And there was a pairing strength in the theory, which was labeled lambda, but they acknowledged that it was phonon attraction plus Coulomb repulsion, some smaller Coulomb repulsion. So actually I put it here as lambda star. And so the TC equation that comes out analytically in BCS theory is a constant times a scale of phonon frequencies times e to the minus 1 over lambda star. And omega is the maximum frequency for this assumed attractive interaction between electrons. There, it might be equal to the maximum phonon frequency, or it might be 50% larger than that, something like that. But this is the equation that they obtained, a simple exponential for weak coupling. And from this equation, it's favorable to increase either the frequency or increase the coupling strength, or both, preferably both. 1960, Migdal published, and then Eli Ashberg published the same year in the Soviet journals. What Migdal noted was that in the diagrammatic theory of condensed matter, which was just being developed in the late 1950s, mostly in the Soviet Union, that because the mass of the electron is so much smaller than the mass of the nuclei, and it's really much, much smaller, the expansion parameter in diagrammatic perturbation theory is the square root of that, but that's already very small. It's a very good expansion parameter. So all you need to do in terms of these Feynman diagrams is to include the simplest bubble diagram. This is the electron self-energy. It's an electron of momentum p, here emitting a phonon, and then reabsorbing the phonon here, and coming out with the same momentum. This is a virtual process. It happens even at t equals 0, when no phonons are excited. A similar thing for the phonon self-energy. What Eli Ashberg did was to take this theory and generalize it, include an off-diagonal Green's function, and in terms of diagrams, what you see is these arrows here for the normal state all point in the right going direction. In the anomalous Green's function, or the anomalous self-energy, what you have something was that he represented by a line with arrows going both directions. We won't go into that. But this is the theory of superconductivity, which has been generalized over the years. So in 1964-65, Scalapino, Schrieffer, and Wilkins generalized this theory of superconductivity to a theory of strong coupling superconductivity. BCS was weak coupling. And moreover, they generalized this to a type of theory that could be applied to real materials. This is the complicated equation for the frequency-dependent energy gap in the superconductor at T equals 0. This is the comparable equation in BCS theory for finite temperature. This is the Fermi function with temperature in it. And here you see the gap here, and the gap in the denominator as well. And if you just look near TC, where that gap gets very small, this drops out. You get a linear equation for the gap, which you can then solve for TC as a function of the parameters in the Hamiltonian, which I just showed you. TC equals frequency times the exponential and minus 1 over lambda. This is actually the equation for T equals 0. For T greater than 0 up to TC, there are Fermi factors occurring here and there, and a Bose factor occurring here, which makes these more complicated. I will return briefly to that. The problem was that here was a good workable theory, but there was no good theory of the electronic structure of materials in 1964, 1965. And that's, in fact, what I worked on during my PhD thesis in 1971 to 75, was just understanding the electronic structure of transition metals better. Neil Ashcroft is quite well known in this area of hydride superconductivity. He had predicted in his thesis in 1964, and then published in PRL in 1968, that metallic hydrogen ought to be a very high temperature superconductor. He didn't give a number because he didn't know the various parameters for metallic hydrogen. Well, it got to be around the turn of the century, and it was learned that it was harder to produce metallic hydrogen under pressure than had been suspected. And he wrote this second paper, Hydrogen Dominated Metallic Alloys, High Temperature Superconductors, again, question mark, with the idea being that if you start with molecules and compress them, you get some pre-compression of hydrogen. You push them together, you cause some chemical reactions to occur, and you might get high temperature superconducting behavior from that. I'll just mention that I gave this talk in New Zealand once, and mentioned that Neil Ashcroft got his BS degree from the University of New Zealand. And after the talk, 2 or 3 of the faculty members at the meeting thanked me for pointing out that Ashcroft was a New Zealand product. In fact, in the early 1960s, the university system was reorganized, and this is now what's called Victoria University in New Zealand. Finally, toward the late 1960s, things began to happen in electronic structure theory with 2 papers by Hohenberg and Kohn, shown here, giving existence theorems for the energy of an interacting electron gas in an external potential. Existence theorems, and gave an expression for the energy functional, and they also proved that if you minimize this functional with respect to the density, then the energy would be the physical energy of the system, and the density that minimized it would be the physical density. And Sham and Kohn generalized this to an actual workable, self-consistent procedure to solve these equations. Okay, so electron-phonon coupling theory encodes. So first of all, for density functional theory, DFT, it was in the late 1970s when self-consistent calculations began to be done. using this one electron procedure of sham and cone. And these codes began to be put together and with contributions from various groups over the next 30 years. Nowadays, a few of these codes at least have the capability of calculating the phonon frequencies, these phonon branch diagrams that we use a lot these days, and electron-phonon coupling codes in this century of the last 20 years in a few of the codes. And so it's possible to calculate what is needed to actually do calculations, predictions of superconducting materials. Okay, in the late 1960s, Bill McMillan produced a seminal paper. One thing he did was to define this function alpha squared f, which is, well, everything, TC depends on alpha squared f. The superconducting properties depend on alpha squared f. This is phonon coupled superconductors. And what it is describing is an electron of wave vector k being scattered to k plus q, both on the Fermi surface with these delta functions. This is frequency analyzed with respect to q to get the omega here. And then you have electron-phonon coupling matrix elements, which depend on the electron states, electron energies, phonon states and energies, and all these indices. And this is a three-dimensional integral. This is a three-dimensional integral. So this is still today a computationally demanding thing to calculate for compounds of reasonable complexity. If you just have an element, it's not so bad. So this was introduced, and it's natural for what occurs in there that you define the parameter alpha squared f over omega, integrated over all frequencies. That is the electron-phonon coupling strength. That is also the mass enhancement factor of electrons on the Fermi surface, which is k-dependent on the Fermi surface actually, which had been known since the late 1950s as the Green's function theory of condensed matter began to be constructed and used. McMillan devised this equation. He explained his justification for choosing the form he chose, and it is, if I rewrite it in the way I like to write it, it's a generalization of the BCS form. It's a Dpi theta, which was what was known about phonon frequency scales in those days, divided by a number, an exponential of -1 over lambda minus mu star effective. You can see mu star effective is enhanced by lambda somewhat, but the main new factor is that this 1 plus lambda occurs in the numerator of the exponential, and that is a mass enhancement factor for strong coupling superconductivity. Unfortunately, this exponential form taken over from BCS is turns out to not be very good. But this was a breakthrough in describing superconductors with lambda between, say, 0.4 and 1. And he didn't do any analysis for lambda greater than 1 at that time. An interesting development, because all along it's been of interest to try to understand what can be done to increase the critical temperature of superconductors. In a class of superconductors, increase TC. And 73, I think it was, Bergman and Reiner devised this procedure. So the point is, TC is a functional of alpha squared f. Let's forget about mu star. It's a functional, complicated thing, all those equations, of alpha squared f, but you do have the expression that a small change in alpha squared f is related to a small change, resulting small change in TC by something that's called the functional derivative of TC with respect to alpha squared f. So they wanted to calculate the functional derivative of TC with respect to alpha squared f. The problem that presented itself is that, coming back to this slide, if you look in here, again, the Fermi and those factors, depending on T, haven't been shown here, but the point is, this is a gap equation. There's no equation that says TC equals this, okay? And in physics, it's common in theory to take the functional derivative of something with respect to something else. Usually there's a straightforward relation, TC as a function of whatever it is, the arguments are equal to some expression, which you can then figure out how to take the functional derivative. Well, just suffice it to say that Bergman and Reiner devised a method because they didn't have the right kind of equation. They chose a little bit different sort of equation with a pair breaking parameter in it, which, once this pair breaking parameter was allowed to go to 0, would give you the same result as the gap equation. In other words, they could calculate the functional derivative of alpha squared f with respect to functional derivative of TC with respect to alpha squared f. And this is what they found for the various experimental values of TC and alpha squared f. Alpha squared f had been determined from inverting tunneling data, which has wiggles according to alpha squared f. And what they found was really, really quite interesting. All of these gave the same, very similar forms of the functional derivative, just the magnitudes changed. And the peak occurs at about omega equal 2 pi TC. There's no reason why it's exactly 2 pi, but that's just an easy way to remember. Omega for the maximum point of this curve is 2 pi TC. And so if you could take a material with a given alpha squared f, and you could increase its coupling, its alpha squared f, somewhere in frequency, it's better off to do it right here at this peak. And 2 pi frequency equals 2 pi times TC. That was a conceptual breakthrough and numerical breakthrough, I would say also. And what they also showed was, first of all, if you have Macmillan's equation, in that equation, TC is this functional, very simple function of lambda. And it's very easy to take the functional derivative analytically. And it's right there. And you can evaluate that. And here for indium, it's comparing the actual functional derivative, that's this solid curve right here. And what you get from this expression is the dash curve, which becomes very bad at small frequencies, but actually over this range is not too bad. For mercury, which has a very different looking spectrum, the true functional derivative looks like this, same shape as that. And what comes out of this equation is quite different. It behaves much differently at small frequency for whatever reason. But this is just showing that the TC equation, Macmillan, is not to be taken too seriously, okay? It's a fit to a lot of computational data and some experimental data, but it's not meaningful physical quantity to interpret.
Can I ask you a question?
Sure.
So just try to get the physical, this is work I didn't know about, to get the physical significance of this. If I have a superconductor with a particular TC, it's electron phonon mediated, and I want to increase TC,
Yes.
and I should do that, I should enhance, let's say, the phonon density of states at frequencies which correspond to TC. Is that the takeaway message?
Frequencies.
I don't know how to do that.
2 pi times TC.
2 pi times TC, sorry.
Right.
Yeah. But that's the takeaway message. So I don't know how to do that. But if I could do it, that's what I should do. Other phonons don't matter as much.
That's right. And if you want to increase lambda, what you need to do is increase alpha squared f at very low frequency. And that's a bad thing too. Low frequencies are overvalued by many people still, are overvalued in trying to get higher TC. And I'll try to get to say something about that at the end of the talk. Yeah, so intermediate values of omega.
This is because we're trying to increase TC at phonons near TC. This is obviously some first order approximation, and we don't expect the domain of applicability of this idea to be very large in terms of enhancing TC. It's a small TC enhancement.
Yeah, that's one way to look at it, suspect it. It's also true that in theory of materials, frequency dependent and temperature dependent, that the frequency, there's often similar frequencies, and you'll have some property that depends on omega squared plus, it's not t squared, it's 2 pi t quantity squared. So 2 pi t is somehow a similar sort of scale to omega. And that seems to be what's showing up here. All right. So in 1975, Phil Allen and Bob Dines did a lot of analysis of the Ely-Iceberg equations. Bob Dines was taking tunneling data and inverting it using Macmillan's codes to get alpha squared f for more and more materials. And Phil Allen was solving the equations. And what Phil Allen showed was that Macmillan's equation was very bad at large lambda, and in fact, at large lambda, TC from an analytic solution that you could get in the large lambda limit, a TC is proportional to the square root of the quantity lambda times omega squared, average omega squared. And in terms of parameters we use these days, the omega squared is, I haven't pointed out, lambda for an element is proportional to 1 over omega squared. And what's in the numerator of that expression is the density of states times an electron ion matrix element squared, which is eta, and what's left over in the denominator is the ion mass. So this is what you should aim for if you could ever get up to get into the really large values of lambda. And large, they were thinking in terms of large values being 10 there. 10 is would still be very large in today's world. Well, Allen and Dines refit equations using 200 input numerical alpha squared f's and experimental alpha squared f's, and improved the Macmillan equation by adding 2 prefactors. One is a strong coupling prefactor, the other is the shape of the spectrum factor, and it works much better than the Macmillan equation as you get to higher TC materials. Okay, I'll just mention here that the full Hamiltonian for a crystalline material or any material collection of atoms is easy to write down. It's just kinetic energies and potential energies. So the Hamiltonian is just this operator, which includes the potential functions, the kinetic energy operators, the electron operators, position and momentum. But a typical Hamiltonian you will find in the literature where researchers are trying to learn more about electron-phonon coupling is to have one like this, where it's already got electronic structure in there, here, band structure. It's got some bare phonon frequencies, which are always ill-defined. Electron-phonon matrix elements, which one chooses as one wants to try to demonstrate something, and Coulomb repulsion. These are tracks, these are repulsion, and the problem with this is that, okay, in density functional theory, we can keep the nuclei fixed and calculate the band structure. So this part is okay as it stands, but there's no corresponding bare phonon frequency. And theorists take model Hamiltonians, which do have bare phonon frequencies and coupling, and study these. And they're being studied a lot still. The last 15 years, I've found out, have some very interesting papers looking at the behavior of these model Hamiltonians as the coupling becomes very large. But I contend that it doesn't say anything about the real materials, because in the real materials, there are no parameters whatsoever. They're operators, and they're fundamental constants, E, H bar, and M. And that's where the current theory of ab initio theory of superconductivity starts, with that Hamiltonian. The current best theory, it's not what is used in most codes and most calculations that people use, because it doesn't have to be, but a really solid theory from the ground up is due to Artie Gross and the group members that have come through his group in the last 25 years. He's now retired and gone to Israel. But what he did was to formulate the superconducting density functional theory, which has not only this exchange correlation functional with density that ordinary DFT has and has to approximate, but he had to incorporate two more functionals, one related to the gap function and another one related to the nuclear function. Sort of the diagonal of the nuclear correlation function. But instead of just having the usual DFT self-consistent loop, that's what you start with. And once that's self-consistent, you come down and you go to self-consistent density functional theory with some approximations for these two new functionals and solve those equations, which are much more involved because they involve both electrons and quantum nuclei, and check for self-consistency. No, so you have to go back this loop, and things have changed, so you do this loop again and then back here. So this is a taxing sort of computation. And finally you get the output and you analyze the output. Yes. Okay. So in that case, I'm going to skip this because it's takes a little description. This is application of this theory to lanthanum hydrogen tin, and just say here the experimental data, right here the experimental data, and this is superconducting density functional theory without taking into account anharmonicity and some other corrections that are relatively small. So the corrections are appropriate, they should be made. In actual fact, they decrease the agreement with the experiment somewhat, but still, there's quite good agreement. This is a deuteride. Good agreement there. Not perfect, but good. But again, we don't know that these samples are perfect either. They may be off stoichiometry and so forth. Okay, so here are three of the hydrides that our group studied. The electronic structure we won't worry so much about. I'll just say that this superconducting density functional theory, unlike the Allendine's equation and so forth, it works very well for actually very low TCs. So these are experimental TCs of these elements and the calculated values. I won't say any more about that, but that's sort of a breakthrough of its own. There's no mu star. There is the Coulomb interaction that treats mu. And so there are still complications that a couple of groups in the world, one of them being the self-consistent superconducting density functional theory group, can take into account, which I will skip over. So I'll show you this. Let me see if I can make it. Not quite sure. Maybe I can't. Anyway, this is an ab initio molecular dynamics simulation. Yeah. Maybe click on the picture. It was done several years ago by Antia Botana when she was postdoc with me, in collaboration with expert Francois Gigi. The point of this is that if you can see it, these hydrogen atoms here bounce around a lot. Normally, in one of these simulations, if you would have something, this is sulfur and hydrogen, if you'd have sulfur and, say, niobium or something like that, you would hardly see any motion at all. Here it is. Okay, so that's the hydrogen really bumping around. So it is anharmonic. I think it's anharmonic in all of these hydrides at high pressure. It's just something that requires a correction in the theory, and it's not done very often, but it's something to be recognized and interesting to see. And there are several codes available which people can do these calculations. They're relatively easy to use, and I'd say still relatively easy to make mistakes with. This is materials design, which I'll skip over. And since it's about time to stop, I would just mention here, this is a figure out of the paper by Chan Sui's group, 2014, where they predicted 200-degree superconductivity at around 200 gigapascal. And an interesting feature of essentially all of these hydrides, metal hydrides, is that the acoustic modes down here are all sulfur. You can see a sulfur character and hydrogen, and all the optic modes up here are hydrogen. They're separated. They're just barely separated here, but they're separated. And that means that you can do some analysis on these compounds because hydrogen is so light that you can't do in most compounds. And in fact, that's what I'm going to talk about tomorrow. So with that, I think I'll stop right here and take questions.
Questions?
Students first.
Yeah, go ahead.
Thanks for the nice talk. I have two questions. One is, in theory, how did people include the high pressure effect in the calculation? And the second question is, so I do see that the lanthanum hydride and then H2S is very successful and at high pressure, but the community's final goal is to make superconductivity at room temperature at 1 atm, right? So what kind of lessons can we get from those success at the high pressure?
So let's start with the first question. How to the electronic structure, people include pressure. What they do is take the lattice and then choose a volume that they want to do the calculation at, calculate the energy, and calculate the pressure. So that's standard in these codes now. You calculate the pressure, you calculate the enthalpy, E plus PV, and that's where you get these curves stability and find out about relative stability. Your second question was?
So in theoretical perspective, what kind of lessons can we get from the success of high pressure superconductivity to make 1 atm high DC superconductivity? What kind of lesson can we get from the success of those?
That's what many groups are thinking about. What kind of lessons? And my comment to that is that there have been now lots and lots and lots of published results on pressurized hydrides, metal hydrides, with almost no analysis. Analysis of the type that I will talk about tomorrow. Some of them don't even report the density of states at the Fermi level. They usually will give a curve of alpha squared f in the integrated lambda, omega, and so forth. But when a calculation gives you lambda 4, which is 50% larger than anything that's been measured so far, or in a recent paper, lambda 7, the authors don't pay too much attention to why. Why is it 4? Why is it 7? Why isn't it 2.2 like a lot of other hydrides? So there's a lot of analysis needed for that. It's an open question.
Yes.
I have a general question. So, can you get the possibility of not seeing like mismatch effect? Can you have is there a possibility that you can have a superconductor?
I can't quite.
No mismatch effect?
I can't quite hear.
Can you have a superconductor without a Meissner effect?
You know mismatch effect, yes.
Well, a superconductor without a Meissner effect at high field is a type 2 superconductor. These vortices of flux come into the material as you bring on a magnetic field. That's just something that comes out of Ginsburg-Landau theory. And all superconductors that I know of at low fields exclude the field. Okay, they won't expel a field that's in it at low fields, but they will exclude a field. There's a lot of discussion, a lot of theory these days on triplet superconductors, where you have spin parallel pairing up and down, and they can behave much differently. And there are papers trying to figure out, and it depends very much on the parameters and the type of exotic order parameters you have. There's even a statement in one paper that in one of these triplet superconductors, they can be tuned so that HC2, the upper critical field, diverges, goes to infinity. In other words, you could put an arbitrarily strong field in there, and because it's parallel spin pairing, it'd still be superconductivity. So this is a relevant kind of thing to be looking at.
Some people like ferromagnetism, so like, can we still see like the mismatch effect? Can we be able to see like the ferromagnetic behavior when we are superconducting state? And like yesterday, FQM that presented the paper where he was able to see some ferromagnetic behavior inside the superconducting state. It was quite surprising.
So you're talking about the iron selenide.
Yes.
Iron selenide intercalated with lithium hydroxide, but some iron goes in between, so you get a ferrimagnetic state. But maybe I can just answer. I think you have to think that these are two sort of separate regions of the crystal. So they kind of live independently. So I think what you're asking is, can you have a ferromagnetic order inside the superconductor? You know, they live together.
Your answer to that is yes.
Well, I mean, it's yeah. This is maybe we can discuss after this. There are superconductors that have magnetism present. Ferromagnetism is quite unique. I don't know. Are you going to talk about this? No. Maybe we can talk about it after. Okay. You had a question?
I have a question, but the students.
Okay, any other student questions before? Yeah.
So, so is the like superconducting like DFT like this type of calculation restricted to sort of like a mean field framework? It seems like that like self-consistent field calculation would be unable to capture like more like dynamic correlations or dynamic interactions. So
It is really a solution to the Ely-Ashburg, the Migdal-Ely-Ashburg equations in the superconducting state, including not only dynamic interaction with the phonons, but also the electron-electron repulsion. So the dynamics are all in there that are in the Ely-Ashburg equation.
So, and then I have a follow-up question to that, which was, so you mentioned, I think, with the calculation of the phonon spectrum, that already includes some electron-phonon interactions there. So my question is like, what is the sort of separation between the interactions? Like, what's already included there? Is it like just a screening of the like some sort of screening effect from the electrons, or like how is that separated?
So what I would refer you to is the Reviews of Modern Physics paper by Feliciano Justino in 2016, I think, which is the current holy, I don't want to call it Bible, but it's the current understanding of electron-phonon interaction, including superconductivity, but other things also, starting from the general exact Hamiltonian with just universal constants in it, and how you deal with this question of, which I think is what you're getting at. You can get right away to the electronic structure by holding the nuclei fixed, you get the band structure, the FT band structure. If you hold then the density fixed and calculate the frequencies of vibrating nuclei, what you get are what are called ionic plasma frequencies for the nuclei, which they don't have static screening. We don't have any screening, so they don't have acoustic modes. And they're about a factor of 4 to maybe 10 higher than the experimental frequencies. So that's not a good place to start. And I know it's not a good place to start because that's what I did on my first postdoc, was to start that way and try to renormalize down by a factor of 10. And that's not the way to go.
Your quick question?
Sure. So a question about the notion of prediction here, or even post-diction with this kind of theory. And so, to what extent, with state-of-the-art calculations, with minimal input parameters, and if you have input parameters, what are they? Can you, for instance, post-stick the transition temperature of lead or aluminum? So sticking to simple materials. And then follow-up question is when, so for the slide that you have here, where it said, as I understand, TC is predicted to 200 Kelvin. What goes into that? I mean, I presume a lot does other than just the structure. I'm far from an expert. There are things which are known about pseudopotentials, and those are generated based on some theory, but also presumably based on old experimental data from other things. So two-part question.
Yes and no, but no to the last one. What is done now by more and more groups is to just say, I'm going to work with a binary system, say lanthanum and hydrogen. This is the example for lanthanum and hydrogen. And we don't know what sort of compounds are stable there. So they calculate for a lot of different structures, a lot of different stoichiometries. Here's hydrogen content, 0.6 to 1, and calculate the curve, which is called the convex hull. This is the enthalpy versus content. Here are the compositions that are obtained. The lowest energy are the most favorable. These are all stable compounds. This is the most stable. These up here are not stable compounds. Then you have to do that for the pressure you want, then change to another pressure you want, another pressure you want, and you generate all the structures that you think are reasonable for lanthanum H6, I guess it is here, there. There can be several different structures that might be reasonable, and you look at those, and some groups have ways of using the output enthalpy energies to predict, looking back at previous structures and forming new structures. Computer forms new structures from these rules and try those. So it's a pretty extensive searching of the landscape in a binary system, say, to find the stable compounds and their volumes, their internal structural parameters, and then do the calculations. DFT, phonons, electron-phonon coupling, and TC. So it's strictly with no experimental input whatsoever. You just choose the elements you want to put in there.
So you just have the atomic numbers, that's the only in the calculation. Solves the Schrödinger equation with nuclei and
if you want to,
40 electrons there.
That's right. If you want to do binaries, you choose Z1 and Z2, lanthanum and hydrogen here, and you have these algorithms to go through all of this for given pressure, change the pressure, but for given pressure, yeah, it's without any experimental input.
No experimental. Okay, so then what about the other part? My first question: how well do you do on aluminum or lead?
That was one of these here. So this is only with superconducting density functional theory, because if you use the Allendine's equation, it's wrong as lambda begins to approach mu star. It's wrong. It wasn't fit. It wasn't meant to reproduce that.
So
it's
so
wrong because you'd have to know lambda very precisely and mu star very precisely, because it's a difference of these two.
But that's external parameters. So those are things that you put into the calculation.
Those are things that we calculate lambda, and there are 2 or 3 ways to calculate mu. Mu star is not a fundamental parameter. It's something introduced by Macmillan and used by Allen-Dines to reduce the computational work of solving the Ely-Ashburg equation. So you take account of the fact that the phonon attraction is retarded with respect to Coulomb repulsion, and that gives mu star. So it's not, mu star itself is not a fundamental parameter, but mu, where it comes from, is.
Right.
Okay, so I better stop you guys. You can discuss it after. Yeah. Very interesting, but thank you, Warren, very much.
Yes, that's what viewers.
Yeah. Okay, our next speaker